For millions in the National Capital Region, daily water security is measured by the arrival time of a municipal tanker. The city operates with a structural deficit of roughly 300 million gallons every day. The existing supply network simply cannot bridge the gap between requirement and delivery. To maintain baseline survival, the region mines its historical groundwater, extracting reserves far faster than natural recharge can replace them. This chart shows extraction levels reaching a breaking point. Gurugram pulls 212% of its annually replenishable supply. Faridabad extracts 180%. This over-extraction is coupled with a collapse in quality. Pre-monsoon samples across Delhi now show concentrations of lead, uranium, and nitrates that frequently exceed safe limits. The data shows that this dual crisis of quantity and quality is a failure of management, not a geographical inevitability. The National Capital Region receives a significant natural endowment. Every year, an average of 750 to 800 millimeters of rain falls on the basin. The challenge is temporal. Roughly 85% of that volume arrives in a concentrated 80 to 100-day monsoon window. High-intensity bursts can deliver over 400 millimeters in a single month. Capturing this resource requires infrastructure engineered for rapid, high-volume retention. However, legacy urban drainage was designed for the opposite purpose. These systems prioritize the rapid evacuation of water to the river to prevent local flooding, rather than volumetric capture. When high-intensity rain hits an urban footprint designed only for evacuation, the result is an immediate volumetric failure. The water overflows the drains and pools in the streets. This uncaptured runoff sweeps up street pollutants and mixes with overflowing sewage, flushing a toxic chemical load directly into the river. The region squanders a theoretically capturable 200 billion-liter annual endowment by allowing it to mix with urban waste. Reclaiming that water requires addressing the foundational bottleneck, the combined stormwater and sanitary sewer. Combined systems ruin harvestable rainwater by mixing it with high-nitrate sewage at the point of collection, making it unsafe for storage or recharge. This illustrates the prerequisite for a modern water strategy: three-pipe separation. The brown line routes toilet waste to the municipal network. The green line captures gray water for local, non-potable reuse. The blue line isolates pure roof runoff, directing it to dedicated storage and aquifer recharge. This separation also removes the massive hydraulic load from the sanitary sewers during storms, preventing treatment plants from being overwhelmed and discharging raw sewage into the river. Separating rainwater and sewage conveyance provides the technical foundation for both aquifer recovery and river rejuvenation. Standard mandates treat harvested rain purely as a tool for recharging the ground. This narrow focus overlooks the water's immediate value. Falling rain is naturally free of the heavy metals and geogenic contaminants like uranium and fluoride that now saturate the region's groundwater. We can process this runoff into drinking water using a specific treatment train. It begins with a first flush diverter, discarding the initial rain to strip away pollutants. The remaining flow moves through a multi-stage sand and gravel filter to remove suspended solids and organic particulates. The water is stored in an opaque, sealed tank. Excluding light prevents algal growth during storage. The final stage is point-of-use ultraviolet disinfection, ensuring biological safety without chemical dosing. Establishing a potable tier for rainwater creates a decentralized supply that bypasses the losses and contamination risks of the municipal pipe network. Disciplined engineering transforms the monsoon from a flood management liability into a high-value asset produced at the point of consumption. For surplus rain that exceeds storage capacity, the next step is returning it to the earth. Most installed recharge structures fail because building codes currently mandate a single, generic pit design for every plot in the region. The effectiveness of these structures is governed by hydrogeological determinism. The engineering must match the specific subsurface geology. The Yamuna alluvial plain in North Delhi and Gurugram is composed of porous sand and gravel. This terrain has high primary porosity, allowing water to percolate vertically with little resistance. Vertical recharge shafts are the mathematically correct choice here. The second zone is the Aravalli Ridge in the south. This is hard crystalline quartzite. This rock has zero primary porosity. It can only hold water within secondary fractures and joints. This is why vertical shafts fail here. The water hits impermeable rock and backs up. There is no porous medium to accept the injection. Hard rock requires horizontal surface storage, like check dams and percolation ponds. These pond the water over time, allowing it to slowly find and infiltrate the rock's fractures. Reaching water security requires replacing generic permits with geology-matched engineering. Deploying this model across the city represents a massive undertaking in urban enforcement. Executing this infrastructure model does not require years of drafting new primary legislation. The necessary frameworks, including CGWA mandates and national funding streams, are already active and available for use. The primary task is coordination, cross-referencing building sanctions against aquifer maps to ensure the plumbing matches the ground before construction begins. To maintain this system, a dense network of digital water level recorders can provide real-time telemetry, flagging blocked or non-functional structures automatically. This data-driven model provides a direct path away from our current reliance on polluted, stagnant canals and depleting wells. Capturing 70 to 90 billion liters of rainfall annually would close a substantial share of the city's supply gap, while simultaneously arresting the groundwater decline in Gurugram and Faridabad. True water security depends on the technical discipline to capture and store the monsoon that already falls on the basin.